So I'm Matt Silverlock. I am a co-maintainer of the Gorilla toolkit. So if you've used things like Gorilla Marks, if you use Session, Secure Cookie, any of those kind of packages for like building sort of web applications or services, you've probably used something that I've maybe contributed to or ruined, either way. I also used to work at Cloudflare until a couple of weeks ago. And if there's anything you can learn from this talk, it's that writing a talk, changing jobs, and getting a new US visa at the same time is a really bad idea. And all my flights got delayed. There was a whole bunch of fun stuff, but made it here to Iceland, so can't complain. So I want to talk to you about sort of micro-benchmarking your code. And specifically, I want to talk to you about the things that can go wrong along the way. Without getting too much sort of ahead of myself, Go makes it really easy to sort of benchmark things. And that's great, but it can kind of mask all of the things underneath that can give you some really sort of wrong results. Cool, that's working. So I'm going to talk through sort of what a micro benchmark is. Like, what's the micro part? What's the benchmark part? So think of micro benchmarks as sort of similar to unit tests, right? You're isolating a small part of your code, and you want to, instead of testing it, you kind of actually want to measure it. You want to see like the performance of a particular maybe algorithm, and maybe compare a bunch of different algorithms against each other, right? You want to look at things like throughput, memory allocation, sort of memory allocation or memory usage overall, like each run. And you can compare all that, you can collect all of that kind of data. It sounds pretty good, right? You're collecting data from running these benchmarks. You can make, ideally, data-driven decisions, but that's not always the case, right? That data can be influenced by a lot of things underneath. So there's tons of external factors that can sort of influence those micro benchmarks. And they're really hard to control for in a lot of cases, right? You can run your benchmarks in containers. You can run them on CI. That's great, but stuff like sort of Docker and sort of container systems, all this kind of stuff doesn't always correct for sort of underlying hardware, right? So, how do we control for this? How do we sort of understand maybe that something's actually influencing our benchmarks and causing them to be right or wrong? How do we even know where to start? And specifically, I'm sort of going to dive into showing you how to overcome these kind of challenges. But first, let's do a quick 101 of Go benchmarking, just so we're on the same page. Cool. So, testing package, hopefully most of you have used it in some way. But the Go tool basically exposes a benchmarking flag. It makes it really easy to run a benchmark. You basically call a function with benchmark at the beginning. It takes the testing.b as an argument, which provides basically all of the way for the benchmarking or the benchmark itself to capture runtime, iterations, all those kind of bits and pieces. And so this is basically an example from the standard library. We wrap our code that we want to measure in a loop that runs up to sort of b.n times. And as mentioned in one of the earlier talks, right, sort of the idea is that sort of will run a number of iterations until it stabilizes. But by default, it's only typically about 1 second, and it's sort of rounded up a little bit if you sort of dive through Go source and have a look at how those benchmarking sort of runtime is calculated. Obviously, if we need to do some potentially sort of expensive setup beforehand, maybe we need to go and seed some randomness. Maybe we need to go and just create some objects, create some connections, sort of do some sort of maybe set up some mocks. Maybe you sort of don't want to count those in your benchmark. So you call something like b.resetTimer. Make sure you're actually starting the timer from scratch just before you sort of enter your loop. And it's obviously really easy to forget that. But you should also be mindful of what's considered setup. So you don't want to pollute your results with code that maybe isn't running on every iteration in your real program, but there's obviously plenty of things that you might instantiate on every request or every connection, or there's other bits and pieces. So isolating too much can obviously be sort of unrealistic as well. So just be very mindful also when you're doing a benchmark or you're creating benchmarking code that you're not just sort of freely resetting the timer, or at least you sort of know why you're resetting it. Cool. And just like you saw before, you sort of noticed that these benchmarks are sort of often running for thousands, tens of thousands of iterations, right? And by default, the idea is that like you get a stable result that Go will keep running it until it sees a consistent result. But stability doesn't mean it's accurate. It just means that for that sort of brief moment in time that you ran this benchmark, all of these variables came together to land you on a reasonably stable value, but they can still be wrong. So I'm going to touch on that a little bit later, but just keep that in mind. Cool. Sort of a last part of the recap is we can run specific benchmarks by passing a regular expression to the bench flag. It can also output details about memory allocation through the benchman flag, and you can also sort of call that inside a benchmarking function with b.report allocs or allocations, if you want to report those sort of individually, right? So you can sort of see nanoseconds per operation, bytes per operation, and the number of total allocations for those operations as well. And you can see in this particular case that I'm filtering just the benchmarks with server in their name as well out of Go's TLS package. Cool. So getting those details about allocations is obviously really useful, right? You can identify sort of what algorithms are doing what pieces. You can look at maybe a comparative algorithm that maybe make some changes to. And if you can reduce allocations, you can put less memory in the heap, less work for Go's garbage collector to do, right? So hopefully that improves performance. Now, we often sort of idealize this as zero allocations, right? So, keeping everything on the stack, not allocating the heap at all is like, that sounds amazing, right? That's like no work for the garbage collector to do really at all. My pause times would be super low, my thing will be really, really fast. It's going to be faster than someone else's program over there that like allocates a little bit. But that's not always super clear either. It sounds good, and there's certainly cases that really does apply. But keep in mind when you're sort of running these benchmarks, just like we said here, and you're allocating a bunch, right? You might say, oh, like 146, 185, there's like a reasonable sort of 10%, 15% sort of difference between these algorithms and their allocations. Like that's going to be way better. That's going to be like a 15% less like GC pause times. Nope, definitely not the case. It's really going to depend on a lot of other things, and I'm going to talk through those as we go along. Cool. So, great. So I'm going to talk about these variables, right? I've just mentioned it a bunch of times, like what even are they? So CPU scaling in architectures. We've got assembly implementations. We have things like noisy neighbors, and not just like noisy neighbors in the cloud sense, but like on the same machine that maybe you're just running, maybe just your own CI environment or your laptop. They're all lying in wait, ready to sort of skew your results a little bit. You may not even know that it's going wrong. All right, so different CPU architectures and CPU extensions, right? Like lots of modern CPUs, particularly that on our laptops or modern sort of x86 like cloud machines, are going to have instructions or sort of particular extensions for improving the performance of certain sort of encryption. Cipher suites, things like hashes as well, video decoding even. And although more and more CPUs have those kind of extensions, or some variant of them, potentially maybe not even standardized, it's not always the case. So you need to be really mindful of that, depending on what you're deploying to, depending on the environment that your code's going to be running in. So we talked about before, obviously some algorithms are implemented in assembly as well. Obviously the idea would be to optimize performance beyond what we can maybe do in a language, what its compiler can do at that particular point in time. Except not all packages, particularly in the Go case, have assembly implementations, and then not all of them even have assembly implementations for every potential architecture, right? So you can see in this case, SHA-512, it's great, 64-bit, x86, 64-bit PowerPC, if anyone out there is still using that, and like, is it like IBM S390X, right? So if you're on ARM, if you're on any of ARM v7, v8, if you're on a 32-bit machine, you don't get these benefits at all. It's potentially not going to be just a little slower, it's going to be potentially a lot slower. And that may not even be super obvious, because if we benchmark on our laptops, right, or even a CI environment, but we're deploying maybe for something like Go Mobile, or we're deploying to sort of a Raspberry Pi, or maybe an older Raspberry Pi in particular, that's going to be great. Our laptop's going to be like, cool, yeah, SHA-512, go for it, super fast. We deploy it, and it's like, maybe it's not appropriate for the use case we're sort of pushing it out for. And that's because we thought the whole time that our benchmarks were scientific, we gathered the data, but all along our hardware was sort of tricking us the whole time, and it can obviously, it's not always obvious that it's doing that. Cool. So there's also other things like concurrency, right? So not all algorithms sort of scale directly with the number of cores. So maybe we're benchmarking on our crappy little 12-inch MacBook like I got here with like 2 real cores, but I'm deploying to a 32-core server. Things might be great here, but it might start to sort of fall apart or lose sort of the benefits over another algorithm that I'm benchmarking as we're scaling those cores up, right? There's things like mutexes, all that kind of stuff. There's potentially I/O contention as well. I can sort of start to eat in that and make our benchmarks a little less realistic. There's also interesting stuff like Intel's Turbo Boost, right? So that's, and related implementations on like AMD chips, sort of ARM-based chips as well. I think Apple does it in their 64-bit ARM chips as well, where under particular conditions, so maybe only half the cores are being used for a certain piece of software, maybe the CPU, maybe the machine's running on like AC power instead of battery power, we might burst up a little bit, right? We've got more power available to us. We may be running a little bit cooler because not all of our cores are running at the same time. So that sounds awesome, right? But we don't want to be like running benchmarks, have the CPU turbo boost during like our first benchmark, and then be throttled for subsequent benchmarks. Like, how do we even know that's happening? It's actually really hard to get the direct like frequency of the CPU at a point in time by conventional means, right? The idea of the operating system is to give you a consistent frequency that's reporting back. You have to sort of dive a few levels deeper to get what it's turbo boosting to. It's meant to be this invisible thing that improves your performance. But sometimes you actually want to know what's going on, maybe even disable it, right? Or and find another way to compensate for it if you're sort of running these benchmarks. Cool. So it's really important to remember that the order in which you both write and then run your benchmarks really can change the output of sort of your benchmarks, right? When you write benchmarking code in Go, you're writing it in source files, and you run go test bench. It executes them top to bottom. Like, cool, why not? But what happens if every time you're running it for a few moments, you've just been in your editor is like Vim, and it's not using a bunch of CPU, and you're just like, great, I'm going to spin up and turbo boost. And that first benchmark always gets the benefit. How do you know that, right? Maybe there's a way we can sort of look at in the future to randomize the running order of those, but maybe keep the results sorted so that when you're doing a git diff and you're actually maybe contributing those back into some source control, that you're not getting these like random diffs every time where someone's just changing the ordering. But it might be useful to obviously shuffle that order across multiple runs. Cool. So we also have noisy neighbors in shared environments, right? And a shared environment's also your laptop because you've got a whole bunch of things running in the background. You've got sort of backup stuff, you've got like Spotlight indexing if you've got a Mac, you've got a browser that's like chewing up things when you load like a heavy JavaScript page. Like this little MacBook here, it's a great little machine for developing, but I can skew the benchmarks just by opening like something even simple like Hack and Use, let alone like Facebook, which just completely spins the CPU up, right? And we can see as I am browsing the internet in Firefox, you can just watch my benchmarks just go all over the place, particularly for the longer running ones, which spend more time on the CPU and basically get impacted by the CPU trying to do other tasks. So we're seeing this just ridiculous sort of scale of like 3,100 nanoseconds operation down to a comparatively more normal 1,500. But if we were just running those benchmarks and you're like, okay, well, I don't run them on my machine all the time, I run them in CI. What if the other tasks on the CI machine are benchmarking stuff? What if they're running sort of other CPU-intensive tasks? We're going to end up seeing this kind of stuff, and how do you know that that's actually the case, right? Like this one-off benchmark, how could you possibly know that it's going to be wrong? There's other things like, as well, sort of CPU cache performance, right? When you're running this benchmark over and over and over, that's sort of like best case for the CPU in a lot of cases. So you're not contending with context switching, you're not scheduling other Go routines around that sort of benchmark for the other parts of your software that need to run. There's potentially not even sort of I/O interrupting and slowing things down as well, particularly if there's maybe some I/O in your benchmarks. Cool. So I think it's really clear that CPU is unpredictable, right? And at best, it can skew your comparisons. At worst, it can make them wildly inaccurate, and that's obviously not what we're about. We want to run benchmarks, to get data, to make decisions. Cool. So we've talked a little bit about the CPU. What about Go's own runtime? Like, how does that come into play, particularly, say, the garbage collector, or GC, when we're sort of running these benchmarks, right? Go's GC's improved dramatically over the last few years, particularly sort of since 1.5, when we got a big rewrite and it's now concurrent, which is awesome. And we're not seeing sort of stop the world times much sort of larger than 10 milliseconds in cases even when you've got sort of a heap size of tens of gigabytes, right? Which is definitely out there, but that's a pretty good pause time for this kind of stuff, and it's been trending down sort of release by release. So why am I talking about this? This goes back to sort of what we're talking about in terms of the allocation stuff, right? Allocating less, pause less, because we don't have to sort of go and count more objects and sweep more objects. Like win-win-win. To get sort of these pause times, you can actually sort of run stuff like debug GC stats, and then you can read the GC stats, and you can sort of collect those. You can expose them on like pprof endpoints as well, over HTTP or however you'd like to sort of do that. And you can sort of collect these sort of pause quantiles. You basically make a slice of an appropriate length, and you can sort of do the math to figure out how many quantiles you're getting. If you want like 99th, you've got to make a pretty long slice. But you can obviously sort of break that down and sort of pre-allocate that as well. Cool. So this is sort of what like you'd see if you hit like a HTTP endpoint that had your GC pause times. Obviously trying to draw a relationship between what you're doing when you're allocating. So we can sort of see here minimum, maximum, and we sort of step up by sort of each tenth. And you get some extra data as well. You'll get a long list of the pause times themselves, and then when each pause sort of ended. I've sort of snipped them out here. It was like thousands long on a long-running program. But pause quantile is obviously what we want, and you could obviously filter just for that. Cool. So it's really important to think about the code you're benchmarking, right? Are the reduced allocations between sort of algorithm A, algorithm B, algorithm C, or library A, B, C? Are they meaningfully, I guess, or are they a meaningful amount of the total amount of sort of like allocations of your whole program, or the memory usage of your entire program, right? Are they actually going to contribute back to the pause times that we just looked at in any kind of meaningful way, right? We need to be really careful about sort of assuming that a two times or 5 times or 20 times increase in allocations between two micro benchmarks is actually proportionally going to impact the rest of our program. We shouldn't expect that, and obviously a slight spoiler, we shouldn't expect that a 10 times increase in allocations is going to be like a dramatic increase in our pause times, that it's going to be pausing for 10 milliseconds or worse every time. Right? And sort of putting it another way, if your code's not running in a really tight loop, if there's other code in your application that maybe allocates hundreds or sort of thousands of bytes, or just total allocations in general, maybe it's like sort of like reading from a database, where you're maybe pulling in a bunch of objects and sort of creating a whole bunch of data. What if it's regularly spending time with the network, or just doing any kind of I/O? Be very wary about sort of optimizing for allocations just by having looked at some micro benchmarks. Cool. So let's sort of like take a quick look at what we talked about, right? We talked about the CPU instructions in particular, particularly sort of around crypto code, and see if we can maybe quantify the impact. Cool. So slow crypto is like my own really bad fork of like Go's crypto library that disables the use of the AES and I CPU extensions by just modifying the assembly directly, just like return false every time. So when Go's trying to find out if the machine it's running on is capable of like using these extensions before it goes and uses those extensions, it just says false. So it's actually a really bad idea to do this because without ASNI, you have opening yourself up to sort of timing sort of side channel attacks. You really probably don't want to be doing that. There's obviously advantages not just to speed, but also security by having these kind of extensions. But obviously not all hardware has these extensions, and sometimes you still need to go and do something. So I think we see pretty quickly that with our crypto, our slow crypto, we have just like a simple like XORing some tokens, and secret box, which is another algorithm, and I'll talk about it in a moment. You can see at 206 nanoseconds, 4099 nanoseconds. So it's like a 7 times difference from having that sort of that CPU support, which is obviously pretty awesome, right? Like it looks so much better. We're allocating less bytes in total. Like it obviously ran way more iterations because it's just so much faster. How can you go wrong, right? This is sort of what we mentioned before. This is cool when I run it on my benchmark, on my laptop, or it's cool when I run it on like Google Cloud or AWS. But what if I'm deploying to, you know, like mid-tier Android devices? There's a whole bunch of stuff, even up to very recently, that's running ARM v7 CPUs that do not have ASNI. I think iPhones had them. Not that like tons of Go is living on sort of mobile devices today, but it's, you know, stuff like Go Mobile is obviously pushing that out. You know, you're not going to sort of benefit from that. There's obviously older Raspberry Pis as well in a similar sort of case, and lots of little embedded devices that you might be experimenting on. Go can, with its sort of reasonably small footprint, can be great for those use cases, but we don't always get those kind of benefits, right? Even sort of the non sort of hardware optimized, so that's the secret box, which is like the SALT cryptographic library. It's still like 3 times slower. Still allocates quite a bit. It's tuned pretty well, so it's still like 1 allocation per operation, but 80 bytes, right? So like, I think we look at this, right? If we just ran some microbenchmarks, it's like, in a perfect world on a Intel-driven like cloud VM, right? I'm always going to choose AES GCM for symmetric encryption, ignoring some potential sort of risks around it. Highly recommend looking up nonce reuse. It can be very scary and very dangerous with this, but you're like, cool, just on a pure performance thing, I'm encrypting lots of messages, AES GCM every time. It's at least 3 times faster, if not better. Cool, but that 7 times improvement doesn't always carry you all the way through, right? So let's have a look at a case where sort of we got carried away, I think, with microbenchmarking. And then we can come back to the crypto stuff and sort of quantify that as well and go a little deeper. So we basically, this is like one of these things I've been thinking about for a long, long time. And I couldn't think of a name for it. And I sort of called it the Great Go Router Wars. And it's sort of a term I use to describe the churn between like all of these HTTP routing libraries in Go, right? And to be clear, there's nothing wrong with writing a router. You should always feel free to like write code and put it out there and experiment with things. And like, there's lots of neat little bits in a router that can be like interesting to experiment, building trees and stuff like that, that you can sort of learn how to put algorithms that you might have learned in school or learned in textbook or maybe just like have read about. And you're like, how do I put this into like a real use case and see some benefit from it? Like writing a HTTP routing library can tick a lot of those boxes. So awesome, right? And you can like use it for real in your software pretty quickly, right? Because most of us can want to write maybe like a web service of some kind, even if it's just to play with on a machine. But we saw tons of these libraries come out, frameworks, micro libraries, whatever you want to call them, the whole spectrum, right? And performance became this like total battleground for these things. So what sort of drove my interest was like, this seems like an odd place to focus on performance, right? Like, how much time does our application really spend on the routing part, you know, and how many routes do like most services truly have, right? Especially as we move towards like microservices where we're sort of splitting things up, but even like a big monolithic application, right? Like GitHub's API is a good example. Cloudflare's API is a good example, right? There's like hundreds of routes, maybe thousands of routes, depending on sort of parameters and things like that, but there's not tens of thousands, there's not millions of routes. Like 10,000 items in a slice can be pretty quick to iterate over, right? So where does this sort of like performance sort of drive coming from? So this is like a honest impression of what the war did look like at its peak. It was pretty messy. I just steal this from Dave Cheney, who tweeted this at me the other day, and I laughed really hard, so it was good. But the idea of like this zero allocation router became like this like catchphrase. It was like the bullet point in every README for like why you should use my router, and it was like one of the first ones, right? It's like, well, okay, like what about the API? What about like maintainability? What about all the stuff that like makes me choose software or testing? It's like blah blah zero allocation. Okay, cool. At the same time though, like you can see why that sounds pretty good. You're like, if it allocates less, it's going to pause less, and my response times are going to be fast, and my users are going to complain less, or just measure us better. We're going to look better in external benchmarks. Maybe we're being compared to other providers, depending on what your business is. Maybe it's just more bang for our buck at AWS or Google or Azure or wherever I happen to be running, if we're just using less memory in total, right? So cool. So we sort of first saw this all kick off around 2013, right? And this is like an output from like one of the very popular sort of open sort of benchmarking projects that like benchmarks a whole bunch of routers against each other. And lots of these libraries are like embedding a version of this or their own like fork of this into their own like README or documentation. It was like, cool, like we're faster, or like we're just as good, but we have more features. So like what was leading like library authors in particular to sort of emphasize these so much, right? Like were we, sort of just like I mentioned before, were we really seeing improvements in request latency and throughput, through these like reduced allocations? Now we look at these routers, right, and it's like 14, 29, and 12, like why would you ever use those, right? Like they must be trash, like what's the point? They spend 6,000 nanoseconds per operation, like what is, like, it's just absurd. It's hundreds of percentage more, like no idea. But like why do we look at these and go, oh, I'm gonna like cut out all these really slow ones and just use these three in the middle, like 139 nanoseconds, awesome. And I think my sort of hypothesis here is that there's a couple of reasons. That we valued it because it kind of sounds scientific, right? Someone ran these benchmarks. They generated some data, they collected it all, they ran it tens, hundreds of thousands of times, 5 million times, 20 million times in some of these cases. Like, they've run over this over and over again, they've repeated the results, they got some solid data. Like, there must be some truth to it. And some of it was also probably likely influenced by Go's garbage collector in its less mature days. The GC got better at like late 2013, I think it was Go 1.5. So this all kind of kicked off like as the GC got a little bit better, but I think there was obviously some like baggage from the early years, and things could be a little slower. That influenced people, but I really think it was the data side that drove a lot of this. So what is the relationship between these micro benchmarks and our total application performance, right? Is this zero allocation router like going to really like change the lives of our end users and request latency and actually be measurable? So we're going to run some benchmarks, or rather, I've run them before, and then I'm going to show you the results because like I'm not stupid enough to do a live demo. Although Hunter did an awesome one, so credit to him. And we're going to run them on like real cloud machines that like plenty of CPUs. We're going to take the average of like multiple runs because we want to actually make sure like that, and across multiple servers because we want to make sure that we aren't being influenced by noisy neighbors, we're not being influenced by sort of any burst CPU capacity, all those kind of things that can skew these results that we just talked about. We're going to collect all of that. So, using Work2, which is like a HPG load testing tool. Some of you might be familiar with it. It's very cool. We define a target request rate, duration, and a number of persistent connections. And I'm connecting out over the network from one server to another. So it's still effectively a local network, so we're not going too far. It's all within the same, in this particular case, it was all within the same zone on GCP. So we've got like 8 16 gig connections depending on the core count of the machines. And it's obviously nice and fast. So the network is like pretty much as good as it gets without just running on localhost. But we sort of obviously want to reflect like a slightly real use case. And the way work measures here, particularly work 2, is important, right? So we said by setting a target rate that we want to achieve, we get to make sure that every one of those 5,000 requests has a response within a defined latency. A lot of other benchmarking tools, things like Apache Bench, Siege, things like that, just like a best effort, and they just try to like shoot as many requests as possible. That actually means that your sort of upper percentile data ends up being, can be potentially very wrong. And you're sort of skipping these slow requests because you're just sort of best effort sort of attempting it. There's a whole discussion around this called sort of coordinated omission, and I definitely recommend you go and read into that in the future, because it will help you sort of, when you're measuring these kind of services, measure correctly and actually get your upper percentile data to be correct. So I ran a lot of these. I wanted to collect the data. You know, what am I getting? So we looked at sort of 3 of, instead of like the 20 routers, looked at 3. I looked at GorillaMux because it's pretty old, and it has like a bunch of like regular expression matching, and it makes it like obviously slightly slower than these kind of benchmarks. I looked at HTTP router, which is lots of features, super fast, you know, very few allocations in general, depending on particularly how you use it and what routes it's matching. And just a standard library, right? The standard library doesn't do anything fancy at all, which is why a lot of these sort of routers sprung up, and that's totally fine. But the standard library is like clearly much, much better in terms of metrics than the other 2, right? So we should see that completely demolish the other 2 in our benchmarks. So we ran this a lot. It took a while to repeat this. And we can see, like, as a recap, right? We really see no like measurable difference at the 99th percentile, right? We're talking 0.1 to 0.2 milliseconds across these requests, and like the almost perfect network conditions inside like a single GCP zone on some like pretty hefty machines, right? If you ran this across country, if you ran this across the world, if you were in Iceland, you're connecting back to like the west coast of the US, like that starts to just completely dissolve. So we're already in like the sort of the, I guess the best case for the fastest route, or the worst case if you want to think about it a different way, is we weren't making any database calls. We weren't reading from a queue or like generating any data on the fly. We were just returning like a blob of like static JSON that was just like encoded as bytes and just shipping it straight back out and writing to the socket, right? So like that's as good as it gets. The router's doing like a more meaningful amount of the work. And we still didn't really see a huge difference. Certainly not that like we looked at before, when we looked at these and we're like, well, okay, it's like, how many times are we looking at it? Like 2 times difference from standard lib to HTTP router, like, and even worse for GorillaMux. But we're not actually seeing that when we run it. So from a practical sort of performance perspective, we're not really seeing any substantial difference, right? And again, that's going to be even more diluted when you're actually out in the real world across the internet. So what if you look at some of the GC pause times? Like, were we sort of seeing some sort of lesser pressure there? Maybe it was contributing less to the overall pause times of our program by having this library. And after tens and tens of millions of requests, just as a reminder, we can sort of see the request latency. We see a little bit there, but honestly, like standard lib should have been much better, right? There's so much noise in that garbage collection. It's not always perfectly deterministic, that it becomes obviously pretty tricky to measure. But we weren't seeing that the selection of either of these libraries was like drastically influencing it at all. We would have expected GorillaMux to be far worse, particularly compared to either of the other 2, but it really wasn't. And this is running these things for some pretty long times as well to sort of gather that data. So I think, you know, it's important to realize that the kind of differences we looked at before, when we're looking at this kind of micro-benchmarking data, it can be meaningful. It really can. But it really depends on how those benchmarks and what we're benchmarking fit into our application as a whole, right? If we're just making all this network, like we're writing to the network, or reading from the network, we're going to spend all of our time there and very little time in this library, right? So why did we benchmark it in the first place? Cool. So what else can we use to sort of quantify the impact of micro-benchmarks, right? Like, so they don't sound like super great right now, some of these use cases, right? How can we sort of look at this another way? Maybe make it a little bit more sort of direct. So let's look back to the crypto code. And we've got our 3 algorithms. We've got ASGCM, our slow crypto implementation, which is the ASGCM without any sort of CPU support. and secret box, which is like the X-Salsa20 Poly 1305 construct. It's an alternative to AES, and generally a really good replacement for it. But we're looking at the benchmarks here, looking at the throughput, and slow crypto's the slowest. Secret box, it's not too bad, but CPU sort of enhanced AES GCM is like just completely thrashing them. So what if we measure this in a real application? And it's still a toy application, right? When sort of the line between a benchmark and a real application can be pretty thin sometimes, depending on sort of what you're doing. But in this particular case, we've cut the network out. There's no network anymore. We're just generating 206 random bytes, and I'm running it 10 million times over. We're not even generating those random bytes each loop. We don't want to basically be waiting on dev random each time. We're just generating those bytes. We're discarding the output. We're just writing to dev null. We're not spending a bunch of time writing to our terminal, which can be super slow. So if you have logging and stuff like that, and you were writing this benchmark out, or you're writing all the output here, it would completely skew your results. So we're being very, very favorable to the core sort of encryption algorithm that we're trying to sort of benchmark here. And so I think most of you probably are going to assume that it's probably not 7 times the difference in reality. Maybe 3 times, maybe 4 times. So, what does it come out to? Right, so the difference is really minor, right? We saw a pretty substantial difference even between AES-GCM and secret box. But in reality, we aren't seeing that much of a difference, right? Slow crypto, it's getting there, it's obviously purposely bad. And over long enough time spans, you're going to see this obviously blow out dramatically. But this is the case where I'm just burning through this encrypting messages, right? These 256K messages over and over and over again as fast as possible. There's reasonably few applications that just do that. They're probably reading things off the network. They're probably storing those kind of things. They're probably reading longer messages as well. There's a lot of nonce generation where we're just actually generating the nonces that our encryption algorithms need to actually encrypt those messages. So it's sort of the best case for the fastest algorithm, and it's still really not that much faster than secret box. So, if we actually look at this, you can see that there's actually a bunch of time in a flame graph, so profiling is good. Outside of the sort of the secret box encrypt in this case, we're just actually reading our nonces, right? And the flame graph for our other 2 algorithms is pretty much the same. The slow crypto one, much more time in slow crypto, but for the most part, you can see sort of the crypto ran dev reader read, and we're basically reading off the file system as far as Go is concerned, basically random data to seed our nonce. We're just spending all that time in I/O. That's why at some point, when we go back here, secret box is not that much slower because we're not so much bottlenecked by our encryption algorithm. We're just bottlenecked by I/O. So we can optimize away all this other stuff, but it's not going to make a substantial difference. Cool. So if we wanted to write down a few rules of thumb, what would we ask ourselves, right? So is there a network involved? Are we actually reading from sockets, writing to sockets, both? Is a critical part of our algorithm relying on multiple syscalls or blocking I/O to get things done, right? Is there a database in there? Is there even just on the local machine, maybe we're just reading random bytes as we saw before? Are we allocating large chunks of memory? And last but not least, would the algorithm you're benchmarking meaningfully contribute to the total runtime of your program? If you're writing a program that does some crypto stuff, in this particular example, is it doing it every time in a fast loop for 10 million iterations? If it's not, maybe look elsewhere before you sort of start diving into this, right? And I think critically, and we'll touch on this in a moment, is before you even get to the micro-benchmarking stage, look at the rest of the program and profile it before then diving into the benchmarks. Cool. So what are some of the best practices around micro-benchmarking, right? It still has some use. It still showed us that there was a slight relationship, but not dramatic. But I know, and it's still a useful part of our kit for sort of comparing the runtime performance of algorithms that maybe aren't network or sort of I/O bound, or allocating huge amounts of memory that is out of necessity, right? So the moral story is that you shouldn't give up on them, but you definitely shouldn't obsess over them. So, as I said before, profile first before writing benchmarks. Understand where your program sort of spending its time before you then go in to look at those pieces and see what you can do to optimize and maybe compare your old version versus your new version in a micro benchmark. But say we've got to this point, we're writing these micro benchmarks because we found that this particular part of our program that's maybe spending 50 or 60% of its time is super slow, and we think we have some ideas of how to speed it up, and we want to sort of actually test that. How can we sort of avoid this skew in our results? So we should absolutely benchmark on production hardware, right? If you're running stuff on cloud VM somewhere, benchmark on those. Be very careful about benchmarking on your laptop and then trusting that data and then just like going, cool, I've got everything I need to make a decision, ship it. If you're on mobile devices, like ARM service, anything like that, benchmark on those. You should measure properly. So you should run your benchmarks for longer. Don't just run them for a few moments. Don't just run them for the default bench time. You should actually try and run them for much, much longer. So things like turbo boost are going to sort of even out. You should potentially randomize the order of your benchmarks as well, as much as possible. And multiple runs. You should be collecting this data and averaging out. You should have a look at the differences between your benchmarks so that all these sort of hardware factors that are skewing results, you can have a look at them and come to a sort of a more complete answer. And again, this sort of, I think one thing you probably particularly see is if anyone's used any sort of large enterprisey sort of CI system, there's lots of stuff running at once. You might be waiting for like some build agents to free up. They can be pretty heavily contended, even if you're using sort of some of the open source platforms for CI. It's like, cool, I run my benchmarks every time in a CI system, but again, they can be heavily contended as well, just like your laptop can when you're visiting websites while benchmarking stuff in the background. So be really, really mindful of that and make sure you're running them for much longer periods, again, repeating it over and over. Cool. Use statistics. So Go has a tool called BenchStat that can help you here, right? You can actually just run over and over and over and over benchmarks. And you can see my terrible laptop example here because I wanted to actually average out my results on my laptop so I wasn't just getting like these sort of CPU-influenced results when my thing's turbo boosting all the time. And you have a file that has all your benchmarks, and BenchStat will just aggregate them for you, and it will show you. And we can see that for the most part, it sort of finally stabilized when I ran them enough, which is great. But if you're seeing a ton of variance across your runs, if you're seeing, plus or minus 50% or plus or minus 90%, right? Think about what might be doing that, right? Is it the code itself? Is there some kind of, maybe I/O that it's sort of blocking on, and it's causing certain runs to be slower? Is it the environment you're running in? Is it these things we talked about before about sort of noisy neighbors or CPU sort of throttling or bursting? And I think critically, understand how your benchmarking ties into the performance goals, or sort of service level objectives if you're sort of driving towards that, of your application, right? Like, does what you're benchmarking make a meaningful difference to your application, right? Does it make a difference to the experience of a user? Does it make a sort of a difference to the experience of a developer? Its overall runtime, does it actually just really consume less memory when running on a machine? Or is this tiny slice that you're sort of benchmarking realistically sort of nothing or sort of bottlenecked behind all this I/O that you're doing anyway? Again, as we sort of move towards and deep into a world of sort of microservices and spending more time in the network, there's lots and lots of I/O in front of our algorithms in our sort of code. Cool. So I'm going to sort of opine for a little bit about, not too long, because I know it's getting late, about, what should we care about beyond just micro-benchmarking results, right? And I say this is like both a user of packages and a author of packages, right, is one of the last things I think I run to is running a micro-benchmark. Is I want to write clear code first, testable code. And I want to make sure I'm using sort of composable interfaces. I'm using sort of interfaces exposed by the standard library. I want to make sure there's sort of maintenance. I want to make sure that there's actually people fixing the bugs of this piece of software, right? And maybe those bugs are performance bugs, but I want to make sure the real bugs are being fixed first. And that's not to say that you shouldn't care about performance when it does matter, right? So, I don't think anyone here wants to write like horribly slow code and just be like, yeah, it's good enough because like Matt said, microbenchmarking is like a stupid thing to do. Definitely not the case. But write maintainable code first. Trust Go's garbage collector to do the right thing as much as possible. And profile. And then if you find yourself writing a microbenchmark, think back to what I said before about running that data and collecting it properly. So I think that's pretty much a wrap. I'm going to put the source code up on the slides, that like all the little bits and pieces that I use to generate some of this stuff, so you can have a bit of a look at it. If you have any questions, you can email me at matt@eatsleeprepeat.net. You can like yell at me on Twitter. I think that's what everyone does on Twitter. And I want to give a huge thanks to Chris Broadfoot, Camille Kisiel, Rita Kozlov, and Ryan Jurovich, a mix of co-workers, sort of open source maintainers, and a couple other friends, for reviewing my notes and talk and yeah, all the fun stuff that you reach out to friends to do when you're writing these kind of talks. So again, thanks everyone for coming today and for making it this long. I know you're probably getting all pretty tired and thirsty, and enjoy the rest of your night.